Hey everyone, we're back, and in this lesson we're going to be looking at, given a polynomial of any degree, how can we determine the location of the zeros, and with that, the number of possible zeros. And there are two ways of doing that. In this lesson we're going to look at eventually the fundamental theorem of algebra and Descartes' rule of sign. But first let's look at our situation. We have this polynomial. It's a polynomial of degree 5 with a leading coefficient that's positive. And in recent lessons we said with that information we can get a picture of what our graph looks like. So odd degree, leading coefficient that's positive, we can say the end behavior of our graph will appear as that. But before, our polynomial was factored. So being factored already, we were able to find the zeros, and with the multiplicity, we were able to determine what happens around each zeros, whether our graph bounces off or passes through. So it's not in factored form. We do not know what's going on in the middle here. And so today we're going to look at what tells us, what about the function tells us the location of our zeros and how many zeros we could possibly have. So given in this form, the location of the zeros we do not know. But with the existence or I should say the number of zeros, we do. We've seen this before, and it was said rather quickly in the lesson prior to this that it is close to about saying the degree of the polynomial will be the same as the number of zeros in the polynomial. I'll say it again. So in this situation, being that we have a degree 5, we could say with confidence that there will be, and at the time it said at most, there were at most 5 real roots. That's what we said before. But today, in this lesson, we're going to examine something called the fundamental theorem of algebra. And what this states, first of all, what it does, it informs us of the number of zeros. It informs us of the number of zeros, not the location. That's important to recognize, as this does not tell us where the zeros are located, just how many there are. And here is what the theorem states. A polynomial of n degree has n complex zeros. You might be thinking, complex, doesn't that mean imaginary? And you are technically right. The complex numbers does in fact include our imaginary numbers. So you're thinking I and all of that. But complex also consists of real numbers. So these are the numbers that we're often dealing with. But this theorem states that given a polynomial of n degree, it has n complex zeros. And those zeros could be a mixture of real and imaginary. But for this lesson, our focus is on the reals. Okay, so I'm going to give you a picture of what a real zero looks like, and then an imaginary zero, what that looks like. Let's say we have the graph, let's say we have a cubic. It looks something like this. So given this cubic function, we would say that there exists one real zero that crosses through the x-axis. But up here, we would say that there are two imaginary. Zeros. And we're going to look at more at that later on. But our focus today is locating and determining how many real zeros we have. Okay, so let's think about that for a moment. Looking back about our situation, with a polynomial of degree 5, we can say with confidence now that there will be 5 complex zeros. So those zeros could be a mixture of real and imaginary. We could have all 5 real zeros, or we could have 3 real and 2 imaginary. Those combinations will exist, but we know we have to have 5 exactly. So that is the fundamental theorem of algebra and what it states. So the next concept that's going to help us determine how many zeros exist, so far we're focusing only on existence, not where it's located, is the Descartes, this is actually René Descartes, a mathematician, philosopher, Descartes' rule of sign. So this, what we're about to write, might be a little technical, but we're going to break it down and see what we can do with it. Just like the fundamental theorem of algebra, this informs us of the number of positive and negative zeros for f of x. Okay? So prior to this, we would know how many zeros exist, and then this would tell us how many of those zeros are positive and how many of those zeros are negative. So, Descartes' rule of sign states that the number of positive real zeros is equal to the number of sign changes in f of x, or less than by an even number. So just in writing, this might make little to no sense at all, but it's actually quite, it is quite simple once we look at actual equations and see how it applies there. But this is for the number of positive zeros, that it's equal to the number of sign changes in f of x, or less than by an even number. So the number of negative zeros is equal to the number of sign changes in f of negative x, or less than by an even number. And I should stay here. When we talk about sign changes, what we are actually doing is we are examining the coefficients of f of x. So that's how we're determining the sign changes, is by looking at the coefficients. So what does all this mean? I mean, the whole concept of sign changes, of f of negative x and or less than by an even number, what does this even mean? You're probably asking yourself now, you're probably pausing the video a couple times, or rewinding it just to hear me say it again. So this can sound a little confusing. Let's try examining these two statements, the fundamental theorem of algebra and Descartes' rule of sign. Let's examine it with this polynomial. 4x to the power of 5 plus 3x to the power of 4 minus 2x to the power of 3 plus 5x squared minus 6x plus 1. Now, by the fundamental theorem of algebra, so we'll abbreviate FTA, by the fundamental theorem of algebra, this polynomial has a degree of 5, which means for us that there are 5 complex zeros. This 5 could be a mixture of real or imaginary. This just tells us that there exists 5, not where they're located. So then Descartes' rule of sign. What we get from this concept is, let's write our function down here again. This lesson, you are getting a lot of information in this lesson, so I want to encourage you, if you have not yet already, pause the video, rewind it, replay it as many times as you need to fully understand what's being said, because there is a lot of technical information that you're getting right now. Write these questions down, post these questions on our class page, and we'll try to work our way through it and understand it as we go. Alright, so back to this. So it says that the number of positive zeros is equal to the number of sign changes in f of x, or less than by an even number. So let's see. We're looking for sign changes. So our leading coefficient's positive, then positive, there's no sign change. Then we go from positive to negative, that is a sign change, yes. Then we go from negative to positive, that is a sign change, yes. Positive to negative, yes. And then negative to positive, yes. So how many sign changes were there in f of x? We should see that there were 4 sign changes. So I'm gonna put here a little table. Positive zeros, negative zeros, and imaginary zeros. So what we see here is we got 4 sign changes, which results in 4 possible positive zeros. And then it said, or less than by an even number, which simply means that I subtract an even number, 2, until I can no longer. So we get 4 and then 2. I can take another 2 away and get 0, and I would not subtract again because then we start getting negative numbers. So this is, we have 4 possible positive zeros, 2 possible positive zeros, or no possible positive zeros. That's what it means by less than an even number. So those are the positive zeros, the negative zeros. Okay, so this is f of negative x. I want to remind you something regarding exponents and signs. If we remember, if I have a negative value raised to an odd power, think like negative x cubed, we have seen how it stays negative. But if I have a negative value raised to an even power, so negative x to the power of 2, it becomes positive. The negative cancels away. So negative raised to an odd power remains negative. Negative raised to an even power stays positive. Okay, so let's try this out. So what I'm going to be looking at is the exponent of the term and what it does with a negative. So an odd exponent, 5, means that we have a negative added to x. So we would have positive 4 would become negative 4x to the power of 5. So then we have a even exponent. So an even exponent, when I put negative x into it, it stays what the sign was. So it would stay positive 3x to the power of 4. And then odd exponent, a negative appears, so negative 2 becomes positive 2. And then even exponent, the sign stays the same. Odd exponent, sign changes. And then our constant just remains the same. So say that again, in short, in summary. When you look at f of negative x, all of your odd degrees, 5, 3, and 1, each of their coefficients, their signs would change. Whereas the even exponents, they would remain the same. So our 4 having an odd exponent changed. Our 2 having an odd exponent changed. Our 6 having an odd exponent changed. And then our evens stayed the same. Now, with that being done, we want to look for sign changes. So negative, positive, yes. Positive, positive, no. Positive, positive, no. Positive, positive, no. Positive, positive, no. So we get yes, there is one sign change. There is one, in that case there's one, negative, 0. And since we cannot subtract an even number, 2, and remain positive, this would not change. So we would just have 1 here. So in this polynomial, what can be said is that knowing that we have to have 5 complex zeros, if we have 4 positive and 1 negative, there would be no imaginary, because again our total has to be 5. If I have 2 positive zeros and 1 negative 0, that would leave us to have 2 imaginary. And then if I have no positive zeros, again we still have 1 negative, that would tell us we would have to have 4 imaginary zeros. So each of our rows should equal what we found from the fundamental theorem of algebra, that our total has to be 5 in this situation. Okay? So let's try another. So try looking at f of x, x to the power of 4 plus 2x to the power of 3 minus 13x squared minus 14x plus 24. And from that, so fundamental theorem of algebra, so our FTA. From that, a degree of 4 yields 4 complex zeros. Okay? So our function, f of x, has 4 complex zeros, mixture of real and imaginary. So now, we look at, knowing the total number of zeros we have, let's look at the possible positive, negative, or imaginary zeros. And we do this by looking at or by using Descartes' rule of sign. So let's make our little table here: positive roots, negative roots, and imaginary roots. And as I'm saying roots, just know it's the same as a zero. I'm just two words that represent the same thing. So our positive zeros. We look at our function. And we look at the sign changes from one coefficient to the next. So positive, positive, no. Positive, negative, yes. Negative, negative, no. Negative, positive, yes. So 2 sign changes for f of x results in 2 positive zeros, and we can subtract an even number, or 0 positive zeros. Okay? So let's look at f of negative x. So our negative zeros, f of negative x. Even degrees, our coefficient stays the same. Odd degrees, our coefficient changes sign. So our positive x to the power of 4, negative 2x to the power of 3, negative 13x squared, positive 14x, and positive 24. I think it's good to say right now, the constant term, since there's no variable, the constant term stays the same regardless of what it is. Okay? So even if it was negative, it would remain negative. If it's positive, it remains positive. The constant term isn't affected by that. So we found f of negative x. Now sign changes. Positive, negative, yes. Negative, negative, no. Negative, positive, yes. Positive, positive, no. So we have 2. We have 2 sign changes for negative x, which says we have 2 possible zeros, negative zeros, or no possible negative zeros. Now, we know we have to have we have 4 complex zeros. If I have 2 that are positive, 2 that are negative, I would have no imaginary. Okay? If I have 2 that are positive, none that are negative, I would have 2 imaginary. Because again, our total has to be 4. If I have 0 positive and 2 negative, again, 2 imaginary. But if I have 0 positive and 0 negative roots, then we must have all 4 of our zeros be imaginary. And that's going to be interesting when we have those cases. So notice how I did that. I had 2, 2, which left us with 0. 2 and 0, I'm looking at different combinations. 2 and 0 left us with 2. 0 and 2 left us with 2 again. 0 and 0 left us with 4. So from this information, we have 4 complex zeros. That's the total that we can have with this function. we know the different combinations regarding their sign and regarding whether they are imaginary or real. But at this point, let's end with this. We'll end with this for this part of the lesson. Our function, x to the power of 5 minus 2x squared minus 3x plus 6. So let's make this our function. I encourage you to stop this video as we end the lesson here, use the fundamental theorem of algebra, use Descartes' rule of sign, and determine, first of all, how many zeros exist, and then the type of zeros that we should find. So I should say, again, ending this lesson, we have not yet talked about where the zeros are. Only what type of zeros and how many zeros exist in this function. So I encourage you, after stopping this video, to complete this example and then continue on with part 2. In part 2, we're going to focus exactly looking at a polynomial. Where are the zeros located? Where are the zeros located in this function once we know these two pieces of information? Okay?